And it's my pleasure to introduce Wilhelm Klingenberg. Right? Well, and so Wilhelm will be talking about umbilic points on complete surfaces. So please, Wilhelm.
Thank you very much. Thank you. So this I'm speaking about work of Viktor Toponogov, who in fact knew Professor Sinyukov. They're the same generation. And secondly, let me say that the name of Toponogov is very well known in Riemannian geometry and in sort of comparison theorems. In particular, the T in CAT spaces, CAT spaces, as coined by Gromov, makes reference to Toponogov in the last letter T, the first two being Cartan and Alexandrov, CAT. Anyway, what we're talking about here is a paper that makes reference to a paper, a late paper of Toponogov from 1996, when he returned to a question of classical differential geometry. We will speak today about work together with Brendan Guilfoyle here on the top of the slide that was published in the Gerber Geometry Topology Journal in 2024. So the object that we consider is a classical surface in Euclidean 3 space. We're assuming it to be smooth and of the topological type of a disk or a plane. And we're assuming it to be complete. So that is saying, in a sense, the surface doesn't have a boundary, but points on the that leave compact subsets of this surface also leave compact subsets of R3. So that's a requirement on the types of embeddings of P that we consider. So if you wish, the boundary of the plane gets mapped, quote unquote, to the boundary of R3, to infinity. These are surfaces of the type of a plane that extend to infinity. That's the assumption of completeness. Thirdly, we're assuming that these surfaces are strictly convex. We will consider now the collection CalP of all of such smooth, complete, convex planes in R3. The conjecture that Toponogov stated in 1995 is that on any such surface, the difference of the principal curvatures at the same points, of course, P on the surface, has an infimum being 0. So let me point out, P is non-compact. So we're looking here at this infimum may not be a minimum. And this is the first remark that we would like to speak about here. So the claim of the Toponogov conjecture implies either that this infimum is a minimum, which says that there exists a point, either exists a point, on such an embedded topological plane, for which the principal curvatures do coincide, or there exists a sequence on this surface that would necessarily go to infinity, namely leaves any compact subset of P in the induced topology, for which the sequence of numbers K1 minus K2 tends to 0. The former, namely the points for which these principal curvatures are the same, are called umbilic points. The latter is a notion that was introduced by Toponogov, and he calls them an umbilic at infinity. So we will now look at examples of both of these situations. And here we see down here, in words, the conjecture is that any convex complete topological plane in R3 has at least one umbilic, be it finite or infinite in the sense above. Are there any questions here? I will be very happy to take questions or comments.
No, it's clear. Yeah.
Thank you. So here's a standard example of a graphical surface, right? This is just a paraboloid. And we have an x squared and positive coefficient b, in fact, larger than 1 at the y squared. So this is an elliptic paraboloid, and the graph of that is what we're considering as an example of a strictly convex surface that is a topological plane that is indeed proper in R3. It stretches out, it moves out to infinity in R3. And what we have here, that this surface we can compute has two umbilics. And we give them the coordinates of these umbilics here in terms of b. Now, we will move in a moment to the case that b is 1. But before doing that, which is sort of a rotational symmetric situation, but before doing that, let us point out that if we take any sequence of points P on this surface going to infinity, so this should be the surface P sub B, not the surface as written here, P3 of B, okay? That's just P sub B. So on this surface here, take any sequence of points that leaves any compact subset. Then the principal curvatures individually, kappa 1 and kappa 2, of necessity tend to 0. This is simply sort of that the surface, it's a graph, but the curvatures individually, the principal curvatures, become weaker and weaker, become smaller and smaller. They're always positive, but they become smaller and smaller as we go to infinity. So these individually, kappa 1 and kappa 2, going to 0 at infinity, certainly implies that their difference approaches 0 as we go out to infinity. So in the sense stated above, we can say that this surface PB also has an umbilic at infinity. So what do we conclude? This is an example, P sub B, of a surface in question that has quote unquote 3 umbilics, 2 finite umbilics and 1 infinite umbilic. Here's the story. Yes, P is indicated here in this drawing as a line. It's convex. As we move out to infinity, these points Pn, as we said, the difference of principal curvatures goes to 0. And we have here one on the right and another one on the left, if you wish, points, finite umbilic points. Okay, so here's again this surface drawn in a schematic form, in a perspective shape. Okay, is that okay? So these are ellipses that this surface PB intersects with on planes, on horizontal planes. And we indicated here the 2 points that lie over the y-axis. There's some easy reason that they have to lie over there for b greater than 1. Now, dear audience, the case that I mentioned before, the simplest case, the case that b is equal to 1. So here we have a rotationally symmetric surface, and you see now the origin will be an umbilic. And that's sort of geometrically obvious because we have an osculating ball, round ball, of radius 1, in fact, that osculates this surface at the origin up to second order. So oscillation of second order to a round sphere is what characterizes umbilic points. And here you go. Here we have at the origin one single umbilic, and we still have one infinite umbilic. So here in this situation b equal 1, we have moved from 3 umbilics to 2 umbilics. Well, this is how what Toponogov was investigating. He was asking, well, can we get rid of the finite umbilic? Can we shift this finite umbilic out to infinity? Well, the first thing he tried is he multiplied here this rotationally symmetric surface with a factor exponent of 1 over 1 minus x squared minus y squared that bends this surface up vertically, asymptotically, along a cylinder. And you see, this modification removes the umbilic at infinity. We still have an umbilic at the origin. This surface remains rotationally symmetric. But at infinity, you see, because this surface is now asymptotic to a circular cylinder that's vertical over the circle x squared plus y squared equal 1. One principal curvature will tend to 1, while the other one will tend to 0. You see? So at infinity, this surface no longer maintains an umbilic. So this is now an example of a surface with only one umbilic. Well, Toponogov was ambitious, and he he asked, can we also remove, find an example of a surface that has no umbilic? And then he came up with sort of this surface, of course, here that where we reintroduce the b. This should be 1 minus x squared minus y squared times b. I have the exponent here on the wrong place. Anyway, this surface he has two umbilics, and as he lets b go to plus infinity rather than minus infinity, these two umbilics move out to infinity. So in a certain sense, he proved that this limit as b goes to infinity exists will be a convex surface which only has now one quote unquote umbilic at infinity. Well, this process, there's some analysis involved in this, but it can be made rigorous. Now the question he asked, can we move off this point at infinity to disappear to get an example of a surface without any umbilic point, neither finite nor infinite? Here's a sketch of this modified surface that I spoke about. Well, that's asymptotic to the cylinder. Well, he couldn't find an example of a surface that has no finite or infinite umbilic, and then he came up with a conjecture that such should not exist. We will today speak about the theorem now that indeed such a surface without umbilics does not exist in the regularity C3 alpha. So we're assuming here that the surface is 3 times differentiable, and the third derivative should be alpha Holder continuous. Then we claim and prove that there is no such example. Now, the proof that we give is indirect. And it is based on the following observation. Given an umbilic-free surface, so given, if you wish, a counterexample, which we will then prove does not exist, then any parallel surface. So P0 here is a putative counterexample for which there's no finite or infinite umbilic. Then any parallel surface is also a counterexample, also has no umbilics. So this parallelism of surfaces is clearly is a that's an you know an operation that sort of respects this conjecture. In fact, it respects umbilic points. If there exists an umbilic point on a surface, then its parallel surface also has an umbilic point at the corresponding point. So before I now move on to the method of the proof, let me just remind you what the parallel surface is. Yes? So what you do is you consider the normals of a surface, and you fix a number greater than 0. Often that would need to be small. And then you consider the union of the points on the normals with a fixed distance. Okay? So that may only work out to be a smooth surface for a small distance, because you can develop sort of these type of singularities that are called wave fronts. Anyway, so this parallelism being respecting umbilics or absence thereof leads us to consider the equivalence class of all parallel surface as one object. So, how are equivalence classes of surfaces characterized? I will simply say that they are just the collection of normal lines of the original surface. Because that collection of normal lines will then, you see, for the perpendicular intersections of them, give all parallel surfaces of the original one. In fact, it will forget the original ones. We will just have the perpendicular intersections of those normal lines, defining a family for small parameter, for small, in a small collection of such, of smooth, convex surfaces. Now, these normal lines, the collection of normal lines of a surface, is a two-parameter family of lines in the space LR3. LR3 are all oriented lines of R3. So in that collection of all lines of R3, the normal lines of a surface is a certain two-dimensional surface in itself, again a surface, submanifold if you wish. Now the umbilicity of a perpendicular surface P0, say, is reflected simply in a in rotational invariance up to first order about one of these normals. That's exactly what osculating up to second order of the surface is. That will result in first order invariance under rotation about one of these normal lines in the family of all normal lines of that surface. Now, this structure of rotation by 90 degrees around this a particular collection in LR3, it gives rise to a complex structure. And that will be the method that we use. We will now then use function theory, and I'll get into details in a second, of one complex variable that rules out the occurrence of such functions that would be nowhere holomorphic, where holomorphicity at a point corresponds to invariance under this rotation by 90 degrees of lines around a particular line. Okay, now we will, so that's a rough in words outline of the proof. And now let us be a little more detailed. So we spoke about this collection of all oriented lines in R3. So these are, if you wish, the collection of all geodesics, straight lines being geodesics, with an orientation, so rays, if you wish. And that collection, as before, we will denote it by L of R3, and the elements of such are small l's here, which are certain subsets of R3, namely geodesics, together with an orientation. So these are rays. And please note that given such a ray in R3, we can associate to that its unit direction vector. So there is a point in the round sphere of R3 called pi of L, which indicates the unit direction of this geodesic. So this is something like the Gauss map. It's something like a Gauss map, not on a surface, but on the lines, on the normal lines, if you wish, of that surface. The second item associated to a point L in this space, LR3, is a vector in R3, which is simply the distance vector of this line to the origin, the minimal distance line. So that will be a line V, a vector V, that is perpendicular to this line. So that's pi of L perpendicular to V. And that tells you how far away this line, by what vector this line misses the origin. Okay? Are there any questions? I think there will be a picture in a second. Anyway, so we have these two entities associated to a point in LR3. The first entity is its direction, pi of L, and the second is a point in S3, pi of L, and the second is a vector in R3 that is perpendicular to that point, to that unit vector. So will you now agree that we have here an association, a map of lines to their unit directions and distance vectors from the origin? The pair of this is just a tangent vector to S3. Is that okay? The pair of these two items are just a tangent vector because V is perpendicular to pi of L. So here's the picture. Here's the picture that I was promising. So you see, we have a line here on the left in R3. That's this left line pointing upwards in R3. We have the pi of L, which is a vector at the origin, a unit vector. That's the unit direction of this line, and v, it's the minimal distance vector, which is perpendicular. Now just shift this vector v to the tip of pi of L, which is a point in S2, and there you have it on the right, a tangent vector to the unit sphere in S3. Are there any questions about this? So this is, if you wish, a parameterization, or a coordinates or something, if you wish, a model space for this space of all oriented rays in R3, namely TS2, the tangent bundle of the round 2 sphere. Here, proposition now is that though that's a diffeomorphism, if we agree on some reasonable differentiable structure on this space LR3, then that space would be diffeomorphic to TS2. And the structure now that will be important in our consideration of umbilic points is just the complex structure on TS2, which is the tangent complex structure of S2. So we have here a small j that is just the conformal structure on S2. The small j gives rise to a capital J, which will be a complex structure on this four real dimensional space TS2. And this complex structure that arises by this rotation, as we indicated before, is the one that arises by as a rotation, as we indicated before, and will be just also denoted by T10S2. That's just another word for this complex structure. And that's the T10S2. That's sort of a sub bundle in the tensor product of the complexification. And that encodes, as we said, the rotation about lines in R3. Namely, this J is the linearization at one line of the rotations about that line of all lines. Now, I said that we will use complex analysis to solve this problem. Namely, we will show that certain functions do not exist, namely functions that are associated to counterexamples of the Tupunova projector. Now we will speak here about the functions that we're looking at. Please consider a convex surface plane proper in R3 P as we began with. Please consider the collection of all of its normal lines NP, and as we said before, that will be a two-dimensional surface in the four-dimensional manifold TS2. Namely, that is the collection of all those lines that intersect P perpendicular at some point. Now, P being convex implies that the map pi is injective. All normals are achieved only once because this surface is convex, where the surface doesn't turn back on itself, sort of. And therefore, this map pi, which is just the projection to the base of the bundle TS2 to S2, it's just the projection to the sphere that is injective. And this implies now that for convex surfaces P, this NP is a section of the bundle TS2 over S2. So have I lost all or many of you so far? Are there any questions?
No, it's clear, clear.
Yes, anybody
Yes,
else?
yes. No, no, it is clear, Wilhelm.
Thank you. Thank you very much for confirming. So here, what is now this the sort of the partial differential equation that we consider? See, we consider now the partial differential equation that is associated to this NP, associated to this section of TS2. Namely, we consider maps small f of the disk in the complex plane and its boundary to TS2, which is a two complex dimensional space, and comma, the boundary of these disks will be required to lie in the normal lines of our surface. Okay? Okay, so we're using these surfaces as boundary conditions for holomorphic functions into TS2. So here is now the requirement del bar f equals 0. Del bar f is 0, that's just df post-composed with j minus j times df, and we're requiring that to be 0 for all points in the disk. So that's just the Cauchy-Riemann equation. That's the first star. That's the first requirement. We're requiring that this f satisfies the Cauchy-Riemann equation. Now, please notice, f now is not a function really, but it's a vector. If it's a map into a manifold, right? It's a map from C into something that's like C2, right? Because this TS2 is a two complex dimensional space. So this is not a function, but it's a map. And in fact, it's called a holomorphic curve. So in analogy to a real curve is the image of a real, of R into, say, the plane. And here we have a map of C, or a subset of C, into C2, like, two complex dimensional space. And we're requiring that to be holomorphic, so that is called a holomorphic curve, quote unquote. The second requirement is that the boundary of this holomorphic curve, namely for z and the boundary of the disk, we want our values of f to coincide with this surface NP. So this the star and 2 star is a well-posed elliptic boundary value problem called Riemann-Hilbert problem. So that's, if you wish, sort of like a function theory, a well-posed item. Okay, so there are solutions, the solutions are manifolds, etc., etc. And here is a picture. Okay, I hope this is helpful. So the NP is a surface, but we're indicating it as a line, as a horizontal line. And it's a surface which is a section of TS2, which is on the right, subset TS2. Now, F is a map from the disk in C, and its image we're indicating also as a line, because it's also two-dimensional. And a curve, if you wish, and we're requiring its boundary to lie in NP, right? So that's the simplest way of indicating the objects that we are looking for when solving the Riemann-Hilbert problem associated to a convex surface P in R3. Here we go. The surface, the equation star is elliptic, and double star is an elliptic boundary condition. It's a Cauchy-Riemann equation, and it's an elliptic boundary condition for the surface. And so the analytic framework sort of for setting this up is just you consider all smooth sort of sections, sigma. So those are all PNs, all boundary conditions, and then we consider smooth maps, respecting those boundary conditions. And then we consider in this set F of smooth maps, the holomorphic ones, right? And then we have a projection of holomorphic ones to its boundary conditions that satisfies. So these are sort of associated operators. And the point here is that this operator pi is a Freitom operator of Banach manifolds. And that's Freitom is just a code word for elliptic boundary layer problem. And its linearization, that being elliptic, so this means that this is a Freitom operator, the linearization of this pi, and that is just saying that the linearization has a finite dimensional kernel, finite dimensional co-kernel, and a closed ring. And as a map of linear Banach spaces at the linearizations, this has a closed range. So that is just the Freitom theory associated to this boundary value problem. And here you have it. Up here we have all solutions. We're assuming we're looking at the collection of all solutions of the Riemann-Hilbert problem, and we're mapping them to just their boundary conditions that they satisfy. And this map pi, the linearization of that has a kernel, which is just the tangent space to the solution space, and the dimension of the kernel is the dimension then of the set of solutions. And now the index of this Freitom operator is just the difference between the kernel and the co-kernel of this Freitom map pi. Now the Riemann-Roch theorem in this situation tells us that the index is just the number, is just the Maslov index of the boundary curve of F on sigma plus 2, where the Maslov index is a certain loop, in the symplectic group modulo the orthogonal group, and which has a fundamental group Z. Now, our theorem, which can be called a regularity theorem for this operator pi, says that is the following. Assume we have a counterexample to the Toponomov conjecture. Assume we have, namely, a surface for which the infimum of the differences between the principal curvatures is not zero, namely greater 0. Assume we have a homomorphic curve, F, that, in TS2, whose boundary values lie in this counterexample. Then, we have here that in a neighborhood of this point NP0 in S, we have that the co-kernel vanishes. The co-kernel of this operator vanishes. And secondly, we have that in existence, we have solutions of these, of this Riemann-Hilbert problem, and the two of those now give the proof of the Toponomov conjecture, which I will just give an outline of. So again, we have a regularity theorem, namely that the co-kernel vanishes, and we have an existence theorem that there are solutions. The proof now is as follows. Assume we have a counterexample, then there is no finite or infinite umbilic point on P. This now implies that the normal lines of P, being a surface in TS2, has no complex point, is nowhere holomorphic. That this counterexample, the normal lines, is a function that is nowhere holomorphic. And a perturbation then will be a regular value of pi of this projection in the solution space. Now, sigma being simply connective, the Maslov index of any loop vanishes. So the Maslov index is just the sum of all complex points, but we're assuming there are no complex points, which is saying there are no umbilics. So the Maslov index of this problem will necessarily vanish. By regularity and existence, we have that the index is dimension to the kernel. By the Riemann-Roch theorem, we have that the index is equal to the Maslov plus 2. Maslov index, because it's totally real, there are no umbilics, is 0, so this is 2. So we have a two-dimensional family of solutions. Since the automorphism group of the disk, which leaves solutions invariants, is three-dimensional, that's just the Möbius transformations of the disk, the unparameterized set of solutions is 2 minus 3, which is minus 1. So the conclusion is the space has dimension -1 of solutions, and that's a contradiction to the theorem that we do have solutions. So these solutions cannot exist because there are no umbilics, but there is a general existence theorem for these holomorphic disks, and that contradicts the assumption of the counterexample of Topoganov. Thank you very much.
Thank you very much, Wilhelm. Thank you, very interesting talk. Thank you. Yes, please, dear colleagues, any questions, comment, remarks?
Can I ask questions?
Yes, sure. Yes.
I want to ask how many umbilic point have a surface which is homomorphic to sphere, closed surface. Is this number depends of convex or not this surface?
Well, for a sphere, you see, for a sphere, there are examples of surfaces that have infinitely many umbilics.
No, not sphere, homomorphic to sphere. For example.
Homomorphic. But there will be examples where every point is umbilic, so there will be examples of infinitely many, and there will be examples where there are only two, namely the rotational symmetric ellipsoid.
Okay.
Yes. So anything between 2 and infinity.
Okay, thank you.
You're welcome. You're welcome. Between 2 and infinity. And of course, it's a good question because here we have for a plane, which is sort of like half a sphere, right? A disk is half a sphere. We have one. We have one. And of course, the point of all of this is that that's one more than is topologically required. That's sort of this rigidity, that there's more umbilics than would need to be. You see, on the plane, there are vector fields that have no critical points, right? But here we're saying, oh, on these convex surfaces, there exists at least one umbilic. So it's like a critical point of a vector field in some sense.
Okay, thank you.
You're very welcome.
Please, dear colleagues, any other comments, questions? Well, Wilhelm, let me ask you. So this is very close to what happens in Morse theory. So when we have critical points on a manifold, we may have a lot of critical points, but they are bound by Betty numbers.
Yes.
And so the question is possible, and actually it looks very natural that here it is used Riemann-Roch theorem or Atiyah-Singer theorem on index, which are just generalization somehow of Morse theory. but in terms of operators or in terms of some other thing.
Yes.
Is it possible to extend this technique to other surfaces, other topological types of surfaces? So I don't know how to even define what is a no, what if you have a torus, what is the convexity? What is the analog of convexity or something like this? Is it possible?
So the real extension of this to other surfaces is floor theory. It's sort of symplectic topology. That's what they do. They consider sort of the space of holomorphic solutions of this Riemann-Hilbert problem in some symplectic manifolds, where the boundary conditions are Lagrangian submanifolds. So I didn't say that. Our NPs are also Lagrangian. I didn't say that. So that's another that will extend this to symplectic geometry. And then they, that's sort of this, Gromov, Eliashberg, Hofer, Fukaya theory of symplectic manifolds, and comma Lagrangian submanifolds. And for that, there is a Morse theory, yes, for solutions of this Cauchy-Riemann operator, yes. And the invariant, yes.
So it is possible to formulate some analogous of Toponogov conjectures in this direction for surfaces with other topological type, or it is hard to say.
You see, this exact case has no generalization to other genus because of as you said, because of the assumption of convexity. But if you drop that and just consider any Lagrangians, which is a weaker condition, then yes. Then you're suddenly in the world of symplectic topology. So if you wish, so that this is some corner, some small corner in this, but it doesn't follow by the symplectic methods because it's a more special assumptions, you see? It's a small geometrical corner of a big theory of symplectic topology initiated by Gromov. Yes. So yes. So this is very special, but it's a geometric situation. You see, it's yes.
Yes, I understand. So the question was because maybe here is no, it looks like this conjecture is just a very specific case, and
Yes.
more interesting in all this theory which you develop is just the theory itself. So the specific
Exactly.
method and combination of them and so on.
Thank you very much. Yes.
And so the question is how much it can be explicitly formulated some other statements about them.
Absolutely. It's the methods. And how can these methods be generalized? Well, it is about this following, Sergei. It is an own theory that is in fact separate from Gromov and Fukaya and so on, because the metric that will be associated on TS2 will not be Riemannian but neutral. So this is some neutral theory. So I didn't say this because there was no time. So you see, if you have a symplectic structure and a complex structure, then they give a metric, right, together. Now Gromov and Fukaya, they always consider the situation that that the Kähler form is positive definite. Here, it's indefinite. It's of the signature plus, plus, minus, minus. So this is exactly sort of the methods it would be interesting to see what these methods mean in this indefinite Kähler symplectic manifolds. Yes, absolutely.
I understand. So maybe next year we will hear.
That's right.
Progress.
It's a different world, sort of. And yes, absolutely, Sergey. It's about these methods. How do they generalize? Where do they sit? And so on. Absolutely. Absolutely, I agree with you. Thank you for saying that.
Thank you very much. Thank you very much.